first speaker of this session is Kuei-Nuan, who is talking about blow-up algebras of ladder or interval determinantal modules.
Thank you for the invitations. So I actually changed the title. Originally was ladder or union interval one, but then Mara prepared this fantastic slide. So I just did a custom of steal her some slide, and then she was going to finish the project. So this is joint work with this is from the two of you here from the Wicca group one, and have result on it, and it doesn't work. Okay, let me do this. No, a couple of collaborators here. Yi-Huang Shen is my long-term collaborator, and this is Wicca 2 group. So the result, and Mara is going to finish the second half of the talk. And what did I do? I just turned it off. Okay. Now the Doki. And one of the Syrian working with another project with Alessandro Castani and Gabriel Sosa. So it's a lot of, but they all, connected, related, I promise. So we're doing introductions. Claudia did a fantastic talk on Monday, actually learned the groundwork about how important, what people care about race algebra, and it saved me time, And what she did is focus on the point and then the variety in idea. So, but today I'm going to focus on modules, right? So you have actually not any modules. It's the direct sum of ideas, okay? And then so you have I is finally generated by some elements, and I'm working on M is the module that is the direct sum of idea I. So this is even more restricted for R copy of I, okay? And then so we're working on the multi-race algebra. So it's IM is just the direct sum of the power of the AI. And so this is the definition of multi-race algebra. And remember, Claudia was talking about finding implicit equation. Yes, so and then that was just finding a kernel, yes, for the defining equation. So I'm going to have a map is R, and I will join the T variable. That's what Claudia's talk, she used Y's. Okay, so there's a T variable. And how many T I should have? I have T 1,1 until S, R, right? So S is the number of generator of I, and R is a copy of my direct sum, okay? And so the kernel of H, I'm going to use the notation. The notation Mara is going to keep using it. Kernel H is the script J, is the race idea of M, and it's also called the defining idea of the race ring IM, right? And remember, Claudia talked about these spatial fiber, which is the image of the birational map. And we have the same race algebra module with direct sum with the K of field is the same. We're doing the same notions. And then again, we're finding the kernel. So we have the map of the kernel. So I have the same T, join the variables, and then K, we'll just do the typo. This is because we two work tonight to combine together, and then so I didn't fix the typo. So it's the psi Tij. This is the psi Tij, not the G. Okay.
Is there one I there, or are they all different?
The same I. Yeah. So we're working on very special case. I guess I'm not so sure how many of you in the afternoon session. I'm not so sure you are sold the idea of getting defining equation is very difficult. And so we are working on a special case that these are copy of the same idea. Okay. So when I is generated by the form of a sine degree, Those ring describe the image, a graph, a rational map between the projected space. That is, she described it. And I think she also talked about the geometry modeling people, care about this because it gives implicit equation. So for computer-aided design people, if you have been David Coase, he is a fantastic speaker. Also, made a connection. And chemical reaction network is something, if you work on the I, is monomials. And then for the direct sum of different I, doesn't have to do the same I, different equation actually give the equilibrium solution for chemical reaction network. And there was a strong field statistics modeling, and you can do the collection of data, and you can encode it with monomial idea and to get the maximum likelihood solution, the degree of maximum likelihood. You can get out of the degree from the defining equations of race algebra. So this is really wide open, very difficult, and many people have said, take a picture. I'm so afraid typo. Now I'm going to just focus on the later determinantal matrix, race algebra of later determinantal modules. So mathematics notation, yeah. So I have n positive integer, and I have n less than equal m. Okay, and for m, I can write it as S, the n partitions, so S1 join S2 until Sn. So there was a partition and interval. And what I'm going to do is, for this matrix, if my entry is inside these intervals, I set it normally as Ij, but it's outside, I set it to 0. And so L, I'm taking maximum minor of this matrix I define, okay? I know this is like very notation oriented. Now this is the picture. She make it, not me. Make it. So this is like my very first interval is U1 to V1 is this one, right? So first interval, and then second interval, third interval, that's what it is. And so everyone else outside the interval for this is 0. That's why I have n interval, because n is my number of row I have. So I'm taking maximum minor. And I'm looking for the maximum minor, the L is taking this matrix, okay? And so observations is, if you look at the just 2 by m case, this is exactly for any m by m is a generic matrix. So I can make stupid interval such that every Si is every one little bit layer. So then it would be generic matrix. But then for the 2 by n matrix, is actually sparse determinant matrix. Is the first project I mentioned from the Kuei-Nuan case. And so all of the result, I am going to, me and Mara, we have all extended to generic maxima case and also sparse case. Okay, that's why I cite a couple of papers from different collaborators. Now, see, this example, I always like the simple example. So I have first row, I have 5 entry only. So this is 3 by A matrix, and is from 1 to A. A is my M, right? 3 by 8. And I have 3 interval, S1, S2, S3. And my S1 is 1, 5. So I have 1 to 5. And then second interval, I have 3, 7. So I only have 3 to 7, right? And third one is 4 to 8. So this is the later I'm working on. I'm finding the maximum minor of this matrix is my ELT idea. Yes? Well, your question, I couldn't hear you.
So the endpoints of the intervals keep the same?
So this is M is the size of matrix, how many column you have. Here have to be
No, no, what
exactly
she's asking
one.
In your case, each interval is exactly five variables, you see, five, and five.
Oh, I made a mistake.
But this is not. doesn't
No,
have
no,
to
no,
be.
it's not. So
It
I,
doesn't have to be.
it doesn't have to be,
I think she's asking, is 3 a valid interval?
3 is 1, 2, 3, it must be 3 row.
No,
No, no, no,
no.
Suppose that S2, instead of being 3, 7, we're 3, 3.
3, 3,
Is that legal?
yes,
Do they have to move strictly to the right? Or can they
yes,
proceed?
yes. You have to move straight to the right. It's like that.
Ladder, but they don't have to be all the same length.
Yeah, so you can do, this is only one spot, it's fine. And then this is any, nothing up to right, nothing up to left. Okay, so next time if I give this a talk, I should change my matrix, make it more, yeah, more variety, yeah. So what I'm doing blow up the later determinant module, right? So I have go back to this is the module I'm working on. I'm working on the multi-race algebra and then spatial fiber. Okay. Now this is the first result. We have the Kuei-Nuan. It was working on idea, not a module. So the case is n equal to 2, right? 2 by n matrix, r equal to 1. And the spatial fiber ring is mod out degenerate Plucker relation. So if you know what the Plucker is, the defining equation of a Grassmannian for geometry people care. And then for the race algebra this is so-called of a fiber type, which Claudia didn't talk about. This is very, very nice case that your defining equation for the race algebra is coming from the defining equations of your fiber, and plus this I shortcut it is Egan-Noska is the linear type part. From the Claudia talk about the T degree 1 cases. Yeah, it's the Mori work, they have the linear present matrix. As long as you have the presentation matrix of your idea, then you have symmetric equation. So this is the defined equation of symmetric algebra. Okay, and then I do not need this. Okay, this me and Yi Huang, this already submitted the same result, but we push it to the module case. Okay, so this is for any size matrix and any copy of R, and this is Kuju Cohen-Macaulay domain. It has a quadratic number basis. Okay, so the significance of the result of this is me.
Lynn, I have a question.
Yes.
In this case, you have copies of the ideal, but the ideal you start with is the same kind of idea
Yes.
that we did with the first project?
Yes.
Or yes, more, it's just 2 by n? Or
No.
3, any size?
Any
n by
size.
n, okay.
Yes, this is any size and any number of copy.
So in particular, you have it for the ideal as well, not just for the.
That's right.
So for the ideal and for the.
That's right. Yes. Yes. So we actually use the so-called Sagabi basis theorem. So we work on the n is the you take initial of each copy, and we found the defining equation for this one, and then we use the Sagabi basis theorem to do the lifting. So the biggest difference from the work of this one, how do you find the K star? Is actually we work on the, you look at the T, A, B is corresponding to the minus. I'm going to use next example to show it to you, and subtract another the mean Jones. So it's like the post-up people doing the incompatible and mean Jones. So we started with generic case. the defining equation is known as Hebbian. And we know the defining equations. And we do the intersections to our later case. And we show this relation is close under the operations. That's how we get the defining equation for the case star. Once we have it, Sagabi basis theorem tell us this is a good number basis after we prove it, and then we go lift that up to go to the minor case. That was the, rough figure proof. And this is different from the kind of different because the finding the defining equation for this part is for any size matrix, so it's different. Now here's the example. Go back to the same matrix. Reminding me, have to change it. Now, typo. Yes, don't change your slide the night before. So, but I promise you will say she did a great job. So I have T available. So I only do the one copy because otherwise it's too much. I have T 134 and then 135, 136. That is corresponding. I take minor of 1, 3, 4. That's what I mean. 1, 3, 5, 1, 4, 5, 6. So I take minor 4, 5, 6. Okay. And then this is known for so-called Plucker relationships. Okay. And I say degenerate Plucker. Yeah. Remember? So what does it mean? Remember, there is no T1, 2, 3 in our case. Why? You take minor of this one is 0. So you take all the possible Plucker and then you literally just remove the one you don't need. So that's why I say degenerate Plucker. And so it's very pretty, actually, from my point of view. And then this is the, yes, I have 2 minutes. I'm going to talk a little bit. This is next 2 slides is completely still from Mara. She typed all of it. So this is another example. And so what we have, the first one, I have 1 to 4. The S1 is 1 to 4. And then we define so-called delta 1 is 3. 3 is 4 minus 1. Okay. The second one is 3, 5, 4, 3, 4, 5 is S2, but my delta 2 will be 2, 5 minus 3. And there was the third one, my S3 is 4 to 7. So this is 3. So what we do have is we compute the analysis rate, which is
How do you get the delta?
Delta is a subtraction of what the S1 is 1 and 4. Yeah, interval is 1 and 4. I just do 4 minus 1.
Okay.
And delta 2, I just 5 minus 3.
Okay, so 7 minus 4 is 3. Okay.
Yes. Yes. I change what you have because you have 3 to 1. And this is the our result of the dimensions of this spatial fiber. It's very simple. It just how many copy you have, and you sum up the delta. It's very cute formula. So this, I remember I say this goes to the genetic case. Yeah. So what we do for the genetic case, because we do the Sagabi basis, we literally just look at the initial monomial. So for the initial, sense, you can just treat the genetic case as the data of this case. And so we really, this is 4, yeah, 5 minus 1. And for genetic case, delta 1, delta 2, delta 3 are the same. And so the dimension for the Grassmannian is delta 1 plus delta 2, delta 3 plus 1, because R is 1. So we really do recover the Grassmannian case. Now this is the last slide, I think so. The Mascaro on his textbook talk about if I have an idea, it's Kuei-Nuan the Hilbert series. The Tina talk about the same one. Then we actually have H1 is the minimal number generated of I minus the analysis spray. And regularity will be equal to reduction number. R is reduction number. A is A emergent and plus the analysis spray is equal to D, right? And then multiplicity is the sum of HI. Now, that's why the other paper with Alessandro Costani and we three have that this is the proof is almost identical proof for what the idea case with a little bit, work to make it work. But this can be extended. And then, so what's happening is Mara gonna talk about algebra invariant. Yeah, so what do we have? We already have an spray. Yes. If we compute the regularity, what comes for free is the A invariant, the reduction number. Yeah, and then she was going to talk about the multiplicity will be another approach, and that's it.